Hey everyone, and welcome back to The Explainer. I am absolutely thrilled to have you here today. We're going to jump right in because today we are setting out on a pretty exciting mission. We're decoding the mathematics of mechanical failure. We're going to take some really complex three-dimensional physical realities and boil them down into clear, actionable engineering insights. So grab your mental hard hats and let's get to work.
So think about this for a second. How do we know exactly where a machine is going to break before it actually happens? I really want you to think of today's topic not as some dry math lesson, but as a high-stakes engineering detective investigation. When a machine component fails, whether it completely snaps in two or just permanently distorts, it's not random. There is a very precise, microscopic point where that failure begins. And today, we're going to learn exactly how to predict structural collapse by hunting down that exact point.
All right, here's our roadmap for the investigation. First, we'll track down the critical stress element. Second, we'll break down 2D stress systems. Third, we'll get into principal and max shear stresses. Fourth, we'll master Moore's circle. And finally, we'll wrap up with a really solid exam pointer for solving these kinds of problems. Let's get started.
Section 1. The critical stress element. Okay, so the crucial starting point is this. A critical element isn't an entire beam, and it isn't an entire shaft. It's a highly specific, microscopic location inside a machine component where failure is most likely to occur. We literally have to zoom all the way in. To predict when something massive, like a bridge or a jet engine component, is going to fail, we first have to evaluate the stress on just one single, infinitesimally small cube of material.
Now, to actually find that proverbial needle in the haystack, we've got a foolproof 6-step procedural recipe straight from our source notes. First, draw your free body diagram. Second, solve for all your reactions. Third, determine the internal loads, your axial, torsion, bending, and transverse shear. Fourth, you want to identify the exact locations where those internal loads are at their absolute most extreme. Those are your critical cross-sections. Fifth, determine the stress distribution at those cross-sections. And finally, step 6, identify the critical element itself. Once you isolate that one little point, you can represent its entire state of stress on a visual element.
Moving right along to Section 2, 2D stress systems explained.
So what's actually happening to this tiny element? Well, there are two fundamental types of stress acting on it: normal stresses and shear stresses. Normal stresses act perpendicular to the faces of our element. Think of tensile stresses actively pulling the element apart, or compressive stresses trying to crush it. Shear stresses, on the other hand, are created by direct shear or torsion. They act parallel to the face. They're basically trying to cut or slice the element like a pair of scissors. And this brings up a brilliant physics concept. If only one pair of shear stresses acts on an element, it would literally spin out of control. So to maintain equilibrium, there always has to be a second pair acting in the opposite direction.
Just to paint a mental picture, imagine our original stress element. Let's just call it element K. It's sitting there in a state of plane stress, which means the stresses on one surface of this 3D element are 0. So we can conveniently analyze the whole thing in 2D. You've got your normal stresses, say a sigma x pulling horizontally at 80-30 psi, while your sigma y is just 0. And then you have the shear stresses, your tau xy, sliding right along those outer edges. This little square is the absolute foundational starting point for all the analysis we're about to do.
Which brings us to Section 3. Principal and max shear stresses.
Now, if we rely strictly on the math to find principal stresses, which, by the way, is the absolute maximum normal stress the material will feel, it gets pretty messy. We're talking about a massive, intimidating algebraic formula. The cognitive load of having to do this over and over, stressing about dropping a negative sign or messing up a square root, leaves a ton of room for error on an exam. It's super abstract. But what if there was a better, more intuitive way to do this?
That takes us to Section 4, Mastering Moore's Circle. Enter Moore's circle. This is literally a visual cheat code that transforms all that abstract math into really simple geometry. Here is the scaffolding to set it up. Step 1. Determine your stress magnitudes. Step 2. Draw your initial stress element. Step 3. Set up your graph axes, putting normal stress on the horizontal and shear stress on the vertical. Step 4. Plot the coordinates of the two perpendicular faces of your stress element as 2 points right on the graph. And step 5, simply draw a straight line connecting those 2 points. Where that line crosses your horizontal axis, boom, that is the dead center of your circle, and it represents the average normal stress.
When you plot those 2 points and connect them with that line passing through the center, it actually creates a little right triangle. And thanks to our old friend the Pythagorean theorem, the hypotenuse of that triangle is the exact radius of the circle.
But here is the absolute magic of this method. That radius is mathematically equal to the maximum shear stress. You get the answer instantly. No complex algebra needed, just basic, straightforward geometry.
Once you have the full circle drawn, you can read the results like a lie detector test for the material. The furthest point to the right where the circle crosses the horizontal axis? Yep, that's your maximum principal stress. The furthest point to the left, your minimum principal stress. The absolute highest peak at the top of the circle? That's your maximum shear stress. You literally just read the coordinates right off the graph. But you've got to remember one absolutely critical rule. Angles on Moore's circle are double the physical angles. So if your principal plane is 17 degrees away in the real world, it's going to be 34 degrees away on your drawn circle. Keep that straight and you're absolutely golden.
All right, let's wrap things up with Section 5. Exam pointer. Solving problems.
Let's put this into practice. Picture a classic exam scenario. You have a cantilevered bar dealing with combined loading. Let's say there's a force P acting axially at one end and a transverse force F pushing upwards. This multi-load setup is the ultimate investigative case study. Your professor wants to know, is this bar going to break? And if so, exactly where?
To completely dismantle a problem like this on your next test, you want a fail-proof workflow. Number 1, isolate the critical cross-section at the wall, because that's usually where the bending moment is the highest. Number 2, calculate your internal normal forces from bending and axial pull, plus your shear forces from torsion and transverse loads. Number 3, sketch out that initial 2D stress element. Number 4, plot those exact values to create your Moore's circle. And number 5, just extract the peak, principal, and shear stresses right off the edges of your circle. Follow this workflow and you turn a terrifying 3D problem into a really straightforward sketching exercise.
There's a great quote from the source material on machine elements that hits the nail on the head. It says, "When the principal stresses and the maximum shear stress are known, the complete design and analysis can be done." And that totally validates everything we just worked through. The hard work of finding these peak stresses is the entire foundation of mechanical design. You now know exactly how to distill really complex, multi-directional forces down to the single most important numbers any engineer needs.
But wait, that actually leaves us with one massive, lingering question. We found the peak stresses, right? We know the absolute worst-case scenario this little cube of material is going to face. But how do we mathematically prove the material will actually survive it? Because finding the stress is really only half the battle. The other half is comparing it to the actual strength of the material itself. And that is exactly what we are going to decode in Part 2 when we get into material yield strengths and theories of static failure. So until then, keep analyzing, keep questioning, and I will see you in the next explainer.